Okay, students, this is the video for uh, bearing numericals. Okay, so we'll start with rolling contact bearing numericals. Okay, so there are type of bearings that you have studied: ball bearing, then roller bearing. Okay, then some special type of ball bearing, angular contact. Okay, then you have studied tapered roller bearing. Okay, then you have self-learning ball bearing, all this. So the deep groove ball bearing is mostly used. Okay, and sometimes a ball bearing is only written, then if it is written in like this in the question, then you consider this as deep groove ball bearing. Okay, deep groove ball bearing with something like that. Now you have understood this dynamic load carrying capacity, okay, for the bearing, and static load carrying capacity. These things are important for a bearing. Static load carrying capacity C, okay, dynamic load carrying capacity, sorry, static load capacity is C naught, static is C naught, dynamic load carrying capacity is C, okay, and then your effective load is P. Okay, P here we write, okay, P effective, and I actually we write only P here. Okay, so this effective load. Now effective load is, if for a bearing, this is the bearing, okay, ball bearing, this is outer race and this is inner race. Okay, then if we have axial load along the axis, also we have a load like this in this way or coming out of the plane, and we have a load along the radius also, then this is called radial load, this is called axial load. If both are present, then we have to find out P equal to x v f r plus y f a. X and y are factors to be determined from data book. V is called race rotation factor. It is 1 if this inner part rotates, inner race rotates, outer race remains stationary, inner race rotates. So otherwise V is 1.2 if inner race remains stationary and outer race rotates. Okay, outer one rotates, inner one remains stationary, like that. Okay, now in most cases V is 1, so we write x fr plus y fa. Okay, your this is your radial load, this is axial load. If only radial load is present, then P is equal to fr directly. If only axial is present, then P equal to fa directly. Okay, these are the things. Now again for bearings we have life L10 we write, this is bearing life for in million revolution. Okay, so number of revolution we count, that bearing will run for this many revolutions, so we start actually write it in million revolution, whatever value in million revolution, that way. That is called life L10. We that sometimes in some book it is written only as L, in your textbook it is written as L10. So L10 is life in million revolutions. And if we write express this million revolution into hours, how many hours this will bearing will withstand the load, that is called L10H. So this will be in hours. So this is life in hours and life in million revolution. Generally this is called rated life, and if you are say asked to find out life of the bearing, then you only calculate million revolution life. Okay, and but if you specified in the question, then find life in hours, then you have to find L10H. Okay, now this is the ball bearing with a dynamic load carrying capacity is given 20.8 kilonewton, is subjected to a radial load of 10 kilonewton. Okay, calculate expected life in million revolution, that 90% bearing will reach. Okay, fine. The corresponding life in hours, if the shaft is rotating as 1450 rpm. Okay, the life in hours, that 50% of bearing will complete or exceed before fatigue failure. All right, so first thing is given is your dynamic load carrying capacity. Okay, radial load is given, axial load is not there, so directly your effective load is P equal to 10 to the number 3 Newton. Okay, now you have to find out expected life in million revolution, so L10. So for ball bearing, this is the relation, L10 is equal to C by P whole cube. C is your dynamic load carrying capacity, P is effective load, and L10 is your life. So L10 is equal to 22.8, this is given as in Newton. So yeah, actually like 22.8 multiplied by 10 over 3 is there, and this is 10 into 10 by 10 over minus 10 over 3 is there, both gets cancelled out, so 22.8 divided by 10 cube, so this is 11.85 million revolution. This is the first answer. Okay, next one is corresponding life in hours. So this is the relation to convert from life in million revolution to life in hours. N is your speed, okay, in RPM. Okay, that is here you see. Now this is L10 is equal to 11.85, and this is here is your L10H. Okay, so L10H is this one, 136, okay, 136.23 hours. Okay, now life complete by 50% bearing is, in general, this is 5 times the life. Okay, for 50% bearing will this is will be 5 times the life that 90% of bearing completes. Okay, so now L10 for 50% bearing will be 5 times the life that that is completed by 90% of bearing. So 5 into 11.85, which is 59.25 million revolution. So this is the answer for the first numerical. Next we'll go to the next one. Yeah, again this life for 50% bearing can be converted to hours using this relation again. Okay, speed is the same, RPM is 1450 only. Okay, and which is equal to this one, 681.17 hours. Next numerical is, for a particular operation radial load is given for a ball bearing. Okay, axial load is not applied, no problem. Then where the expected life is 8000 hour for 90% bearing. Okay, in life in given for hours, life is in hours it is given. So calculate the dynamic load carrying capacity with this when the shaft rotates at 1440. Okay, simple thing. So P is equal to FR, because FA is not present, axial load is not present, radial load is only present. P is known directly. Bearing rated life is this one, L10 is equal to 60 into N is this one, 1460 into L10H divided by 10/6. So L10H is given 8000, L10 is now, that is life in million revolution is 691.2 million revolution. So dynamic load carrying capacity from the relation, that is L10 is equal to C by P whole cube. So C is equal to P into L10 to the power 1/3. So this is for ball bearing only. This relation is for ball bearing. So this is ball bearing. So this is 5000, P is 5000, 5 into 10/3, this is 5000, 691.2 to the power 1/3. This is the value of dynamic load carrying capacity. Okay, next problem. Here we have a ball bearing subjected to radial load is of 2500 and axial load of 1000. Okay, sorry, 1000. Yes, the dynamic load carrying capacity of the bearing is 7350 Newton. The values of x and y factors are 0.56 and 1.6. So the shaft rotates at 720. Calculate the value of life. Now both FA and FR are present. So the dynamic load carrying capacity is given to you. Okay, x and y are given, and n speed is given. So equivalent dynamic load can be found from this relation, although it is not mentioned that whether the race rotation factor is 1 or 1.2, but if it is not given, race rotation factor is 1, v is 1. So x you put the value, fr and fy everything you put here. So L10H now, L10H is you need the value, that is calculate the life in hours. So before that you have to calculate the life in million revolution. So see, from this relation, C equal to P into L10 to the power 1/3. So C is what, 7350, P is 3000, L10 to the power 1/3. L10 can be found using this relation. So this is 14.17 million revolution. Okay, from here again this relation you can find out L10H. Okay, this is for this number. Okay, now we have this one. Select a suitable single row deep groove ball bearing from a shaft which is 75 mm in diameter and rotates at 125 rpm. The bearing is subjected to radial load of 21 and there is no thrust load. Expected life is 10,000. So this is again very simple. Now you have to select a bearing for this one. So look at this. First of all, selection of a bearing can be done once you know the value of dynamic load carrying capacity. Okay, so here you see axial load is not there, so P equivalent dynamic load is P equal to directly that one. Okay, you have a shaft diameter of 75 millimeter. Okay, so you need a particular bearing to be fit so that you can fit that bearing to that particular diameter shaft. Okay, for that first you calculate your life in million revolution using this relation, because life in hours is given. So 75 million revolution. Calculate dynamic load carrying capacity. This is important. So C is equal to P is known, L10 is known. So this is the value of dynamic load carrying capacity. Now you need the data book to select a bearing. because bearings we do not find their dimensions, but we select the bearing from the data book. So for that, go to the data book. Okay, here so this is from this table you have to select it. So for deep groove ball bearing we have two series, series 62, and there is another series which is series 63. Okay, we do not have any more table here available for the data book. Okay, so you have to either select from series 62 or series 63. Now look at this table. This is actually the bearing manufacturer is SKF. SKF is the bearing manufacturer. So this is the famous bearing manufacturer. So we will find SKF bearings in most of the bearing shops. Okay, so they have designations of these designations. This is 6200, this is 6201, 6202, 6203, 6204, 6205, something like that. And these are ISI, the Indian standard numbers for these bearings. Okay, up to these are available. They have not mentioned it, no problem. These are the dimensions. Okay, this small d, capital D, B, R, these are for this is shown here. Capital D is the dimension here, small d is the shaft diameter here. Okay, so this is the these are the small fillet diameters. Okay, so now B is the width here, width of the bearing. Okay, now we'll look into this small d diameter because that is where we will have to fit the shaft. Okay, shaft will come here, right, exactly here. So now diameter is 75, so 75 is this one. Okay, so we have a bearing of 6215. Okay, 6215 we can take. Okay, now here you see for a bearing 6215, these are the values of, see, first this is this column is for static load carrying capacity, this is for dynamic load carrying capacity. This is 41,385, for this one 50,600. Okay, so its capacity 6215, dynamic load it can carry up to 50,600, but in our case this is 88,560. Okay, your dynamic load carrying capacity we need it as 88,000, so 6215 we cannot use it. Okay, so what we can do is we go for next series and say again find out for this one 75 mm. So this is 6315 is your bearing designation here, and look at the dynamic load carrying capacity. This is 89,280. so 89,280 is actually greater than this our required value, so that's why 89,280 is suitable for us, and that we can actually take this bearing. Now 6315 is our selection. Okay, like that. Okay, so similarly I mean if actually we have actually more series that is not available here. Okay, if we let's say that value is 90,000 or something. Okay, we need it for 75 mm, then we have more series, and from that series I have to select it. Okay, like that. Okay, these are called catalogs. Okay, these are manufacturer's catalog, and from here we select the bearing. Okay, this is the bearing selection problem. Now just you have to write like from data book, this is the table, this is the page, and from here you have to select you have selected this bearing. This is SKF 6315. Okay, next is I don't just a moment. Look at this one. Now here you see for a single load deep groove ball bearing, the value of static load carrying capacity and dynamic load carrying capacity are given 2,500 and 5590 respectively. Okay, the axial load and radial load are 625 and 1250. Determine equivalent load, that is P, and life of the bearing. Okay, that is L10 when inner is rotating and inner is stationary. Inner is rotating means V is 1, inner is stationary means V is 1.2. Okay, now X and Y are not given, and you have to calculate them used from the data book. Okay, now look at this. So these are the given values. Okay, fine. So how to calculate X and Y, and we'll look into that. Okay, now so here we have a table for X and Y. Okay, look at this page 381. Okay, 381, and we have a table for x and y. This is values for vxy. Okay, now you have to calculate x. Now see, x is actually for single row bearings, it is written. Okay, so actually if nothing is mentioned, you go for single row bearing. Okay, single row bearings. Now e is small e here is a number, okay, which you have to compare this ratio fa by fr, vfr actually, and fa by vfr you have to calculate fa by c naught. This is actually star is by mistake, it is they have written, and I is also not required. This is fa by c naught only. Okay, so fa by c naught and fa by vfr, this you compare with e. Actually you have to only compare fa by vfr with this value e for each and every value of fa by c naught is given. Okay, so if it is greater than e, then you take this column. If it is less than e, then you go for this column. Okay, like that. Now you see, first of all you need fa by c naught value for this one. Okay, from here you have to get fa by c naught value. Now if you suppose your fa by c naught, that is axial load divided by static load carrying capacity, is let's say 0.084. okay, so for this you have to calculate x. Now x is directly 0.56. if for 0.048, okay, if your fa by axial load by radial load is greater than, you see, e value here is 0.28. if it is greater than 0.28, then x is 0.56. if it is less than that, then this is 1. okay, and if it is greater than e, then you have to get y from here. For 0.084, y is 1.55. okay, for this one. Now if that value fa by c naught we do not get here somewhere, then you have to interpolate between the values. okay, now look at this problem. Now for this problem, fa by c naught is 0.25 and fa by vfr is 625 by 1205, that is 0.5. okay, now fa by c naught is 0.25, so we'll find out 0.25. 0.25 is not available, but we have 0.17 and 0.28, so 0.25 lies between these two. okay, fa by c naught is this column, not this one, sorry, this is here, nothing is written, so this one is the column. So 0.25 lies between these two, so you have to interpolate between these two. That means x is 0.56, that is fine. For 0.17, 0.56, 0.28, so x is 0.56, but y is for 0.17, y is 1.31, and for 0.28, y is 1.15. okay, so for 0.25 we need the value, so for that we interpolate like this. okay, so like this. So from this interpolation, 0.25 minus 0.17, so 0.25 will actually we can write like this. So here we write the values. okay, that is for 0.17, this is fa by c naught, y is actually 1.31. for 0.25, y is unknown, so we keep it like y. So this is 0.28, so this is 1.15. okay, 1.15 is correct. So now what you have to do is you have to interpolate anything you write. So you can take the difference between this and this equal to the same difference. So if you want to take the difference between 0.28 and 0.25, then equal 1.15 here and minus y you have to take. Then you do not take the difference between this and this, because y will be repeated. So you have to take the difference between the known values, 0.28 minus 0.17, this minus this, and then 1.5 minus 1.15 minus 1.31. okay, or else you can take anything else. Like if you want to take now the difference between, if you want to take the difference between this and this, then you can write like 0.25 minus 0.17 equals to this side also y minus 1.31. okay, sorry, 31, because you have taken the difference this side in the numerator, here also same difference. So here 0.28 minus 0.25, sorry, this you do not take because y will be repeated. So 0.28 minus 0.17 only you have to take. So this is 1.15 minus 1.31. okay, so same thing will get actually. If you calculate from here also, you will get y is equal to 1.1936. here from here So 1.1936. So this is the value of y that we have calculated. Okay, fine. All right. Now equivalent load. Now you have v is 1, p x is 0.56, y is this. So we have got p, and from here we know the value of your capital C, that is your dynamic load carrying capacity is given. So this is the value, 57.78 million revolutions. Okay. Now when inner race is stationary, then that outer race is rotating, the v is 1.2. now this will change. Okay, and then v is greater than e again, so we have to calculate this doesn't make any change, so y is 1.1963 only, but here v will change, so your p will change a little bit, 1587.5. previously it is 1446. now your life will change, L10 43.6. okay, and then this is actually not required, but you may find out, it is not written in the question, so L10H is optional here, so L10 only is required, 43.66 million revolution. Here also obviously L10 only is required. Okay, now this is the problem for bearings which are subjected to constant axial and constant radial loads. Now for bearings which are, let's say, they are subjected to loads, okay, where this bearing, let's say, okay, take like this, one bearing is there, okay, under operation, okay, let's say within 5 minutes, okay, for first minute it is rotating at 5000 it is rotating at, let's say, 1400 rpm, and is taking a load of 3000 newton. Okay, for next 2 minutes this load will increase, let's say 5000, and this speed will decrease now to 720. now for the last 2 minutes, okay, it may increase to 7000, and the speed may be let's say 2000 rpm, something like that. So it is fluctuating. In this case load is fluctuating and also speed is fluctuating. Okay, so this is the bearing is now subjected to fluctuating load. Okay, and for that what you have to do is you have to just find out this P effective. Now this is, we will write this P effective only, or sorry, we will write plus PE. Okay, P effective load. Here this is separate, this is different. Instead of calculating like this, we have to calculate PE in a separate, using a formula, okay, that we have I have given you this formula. So using that formula to calculate, we'll look into that, and remaining things are same. Once you get PE, then we can calculate L10 by using C by PE to the power 3. Okay, this one, okay, like from this formula. So again PE only will change. Now for this numerical here, you just read the numerical for deep groove ball bearing. So radial load is, you see, 5500 rpm for 25% of total time. Okay, so radial load is 10,000 for 700 for 50% of total time, and radial load is 7,000 for 400 for 25%. So see, total time is 100%. Okay, whatever time, let's say it is 1 minute, 2 minute, 1 hour, 10 hour, whatever. So for let's say it is 10 hour. So for 25% of 10 hour, for simplicity we take it as 1 minute. For 1 minute, 25% of 1 minute, okay, this is the condition. 5000 is the load and 500 is the rotation. Then for 50% of 1 minute, that is 30 seconds. This is we'll find out how many seconds. Okay, so now this is 10,700, and here again the remaining 25%, that will be 15 seconds. For 15 seconds this is the load, for 30 seconds this is the load condition, and for 15 seconds this is the load condition. That is only if your time is 1 minute. If your time is more, okay, then 2 minutes, then this will be double. Okay, we'll have to actually find out for that 2 minutes, 3 minutes, whatever. Okay, but if the time is not given, okay, generally you have to assume it as work cycle is of 1 minute duration, so that you can actually find out revolution per minute. That is why this is taken as 1 minute. Okay, revolution. RPM means here, RPM is revolution per minute, revolution divided by 1 minute actually, huh? So whatever revolutions we have divided by 1 minute will give you revolution per minute. So that's the reason we take it as 1 minute duration. Now you make it a tabular form. So 3 sets are given. So 3 sets of values of forces are given, and element time is, this is in minutes. So for 1 minute, 25% of 1 minute, that means 0.25 multiplied by 1 minute. So this is 0.25 minute. Okay, so this is 0.5 minute, next one will be 0.25 minute. Okay, okay, now so this is speed is 500 now given, and now what you have to do is revolution for element time. Now this is revolution per minute, then you have to convert this to revolution only. Okay, so now see how to actually convert some revolution per minute to revolution. So you have to multiply with minute some force, so some value which will be in minute. So minute cancel out and revolution remains. So first is this is RPM, 500 revolution per minute. So multiply with 0.25 minute to get this in revolution. This is called revolution. So this revolution in element time. So 125 revolutions are there. Without I mean per minute is not there. So 500 in a minute. So for 15 second, 125 revolutions. So for next one, 0.5 multiplied by 700 will be 350. This is 350 revolutions for 30 seconds, and this is again 0.25 multiplied by 400 is 100 revolutions for 15 seconds. So total revolution is addition of all these. So these are revolutions, n1, n2, n3 are revolutions, and this is the formula to calculate the equivalent load. Okay, so this is cube root n1. This is the n1 is the first that is elemental for first element, the revolution n, this is n1. P1 is the force for first element. So P2 is the force for second element, P3 is the force for third element. So n1 P1 cube, n2 P2 cube plus n3 P3 cube. So divided by n1, n2, n3, addition of them. Okay, so here you see, next is just put the values. So here we have 125 is your value of this revolution. 125 multiplied by 5000 cube plus 350 is your value of the next revolution for element 2. 350 multiplied by 10,000 cube plus 100 here for the third element multiplied by 7,000 cube divided by 575 is the total addition of these all of them. Okay, this is 225 plus 3, that is your 575. Yeah, so 575. So here calculating this we get equivalent load as 8860, and remaining things are similar. Once you get, instead of P, in place of P you write PE. So now from load life, this is called load life relationship. From here you get the life in million revolution, 95.51 million revolutions. Okay, now this is to convert this into hours, life in hours, we need the speed n. So using that relation we get 2768.45 hours. So this many hours it will run. Okay, so there is another numerical, similar type of numerical. A ball bearing is operating in the following cycle for 1 minute. Now this is given, the time is given. If it is not given, then you assume as 1 minute. So P1, P2, P3 is given, 3 cycles, 3 sets are given, 15 second, 20 second, 20 second. Okay, and speed is 1440, 1200 and 710. Expected life of the bearing is 12,000 hours. What will be the dynamic load carrying capacity? Okay, so here C is to be calculated. L10 is given to L10 in hours is given. Okay, so here yeah, you need the n and the speed also. Okay, revolution per minute. Okay, that you have to calculate. Here RPMs are given, so these we'll look into that. Okay, so we need the RPM first. Okay, to calculate this L10. Okay, L10, then we have to get this PE. Okay, and then only we'll get the dynamic load carrying capacity. Okay, so for that, here you see this number of revolutions. So n1, n2, n3, these have to actually see. Let me make a table here for this numerical. 2000, this is element P, okay, 2000, 3500 and 5500, okay. So here again element time in seconds it is given, na? So duration, element time 15 seconds, 25 seconds, and this is 20 seconds, okay. Now speed is given, okay. Speed you write 1440 rpm, 1200 and 710 rpm, revolution per minute. Now if you multiply 1440 into 15, will you get revolution? No, because revolution per minute multiplied by some second will not give you. So you have to either convert second to minute or minute to second, okay. That is up to you. Now if you want to convert, see, 1 minute is equal to 60 seconds, right? 60 seconds. So this here 1 minute, you can whatever revolution per minute you have divided by 60, that will give you revolution per second, and then you multiply with this to get revolutions. We need the revolutions only, n, okay, capital N, right? So either you divide 1440 by 60, 1200 by 60, then you multiply, or you multiply 15 into 60, okay, that will be in minutes, okay. And then one second, sorry, no, either way, this 1 by 60 only, okay. Here 1 by 60 minute, okay. So 1 second is 1 by 60 minute. So here also same thing. So ultimately what you have to do is 1440 into 15 divided by 60. This is a revolution, and here 1200 into 25 divided by 60. Here 710 into 20 divided by 60. So every time you have to do, and you will get the values here. So here you see 1440. So if you actually calculate, this you should get this 360. Let's calculate. 1440 into 15 divided by 60 is 360. This is 360. Yes. Next is 1200 into 25 divided by 60 is 500. Actually a small calculation mistake is there, okay. And then 710 into 20 divided by 60 is 236.467. actually this should be 500 only, and this should be 236.467, okay. So this is the way of calculation, and once you get them, you put them in the values here. You just n1, these are n1, n2, n3, and these are p1, p2, p3. Put their values, and then you calculate equivalent load from this. And average speed, now you see, these are the total revolutions. This one, this one, this one. Total revolution n is n1 plus n2 plus n3. These are total revolutions in 1 minute. So that means revolution per minute. Per minute means per 1 minute. So total revolution in 1 minute is nothing but rpm, revolution per minute, okay. So that's why this is average speed is addition of all them revolutions in 1 minute, that is nothing but revolution per minute, rpm, okay, understood. So this is 1096.47. so you have the average speed, that is n. So n is there, so that is 1096. You put from here, you will get the rated life, that is L10. L10 H was given 12,000, so L10 is 79. Little bit calculation mistake is there, just correct it. And dynamic load carrying capacity, C is PE into L10 to the power 1 by 3, and this is the relation. From here you will get capital C, okay. That is your dynamic load carrying capacity, okay. Now we'll move into sliding contact ball bearing, okay. Sliding contact bearing numerical next. So now sliding contact bearings are those bearings, okay, where we do not have actually this is the shaft, okay. You can just like think like this is the shaft. Here we have a bearing, okay, which is just sliding here. So but in general, sliding contact bearings are not one part, okay. There is connection of two or more parts, or sometimes the bearings are like only half, like only this much portion is present, and this is the shaft. Okay, and the shaft rotates here, no problem, and this is the bearing, only this much is only present. Okay, then this is called, I mean, depending upon the angle from, I mean, angle made by these sides. Let's take a bearing like this. Okay, here, and this is the shaft. Okay, and from here to here, I mean, this is the angle of the bearing. This is the angle of the bearing. Bearing is wrapped around. You can just think like some part is touching this shaft here, and this, I mean, from this angle to this, I mean, from this starting point, this is the ending point, and this is the angle. Okay, so if this angle is 360 degree, it is called full journal bearing. If it is 180 degree, it is called half journal bearing, something like that. Okay, so full journal bearing will take into calculation. Okay, we'll consider if it is not given also, then also we'll take it as full journal bearing. It is written only. So a full journal bearing subjected to radial load of 5 kilonewton. Okay, it is given. So diameter of the journal, okay, this shaft here, this is diameter is given. Okay, length is given. Length is, this is the length. Okay, bearing length is given. Length is 45 mm. Radial clearance is 0.04. Okay, which is actually shown to you here. Just a moment. So this is, here is radial clearance. This is your minimum film thickness. Okay, this was explained to you. So radial clearance is given as 0.04 mm. This is in mm. Actually, this is not written, but this is in mm. Clearance will have a unit because that is a gap. Next, viscosity is 25 centipoise. So you have to convert it to Newton second per millimeter square by multiplying 10 to the minus 9. Okay, journal speed is 2000 rpm. Calculate the minimum oil film thickness and power lost in friction. So here you have to use data book. Okay, in this case. So but first you have to get the most important thing, that is the Sommerfeld number. Okay, this one, Sommerfeld number S, using this relation. Now Sommerfeld number is given as S equal to R by C whole square into mu ns by p. So R is the radius of the bearing. So diameter is 50, radius is 25. Okay, clearance is 0.04 given. So mu is 25 centipoise. So if you multiply 10 to the minus 9, so you will get it as Newton second per millimeter square. Okay, so into 33.33. Now see, this is ns. Ns is revolution per second. Okay, per second. So 2000 revolution per minute is given. So divided by 60 will give you revolution per second, or RPS. So 33.33 RPS. So 33 divided by P is, this P actually, this is the unit bearing pressure we call. And unit bearing pressure can be calculated by from this formula. Unit bearing pressure P is equal to load divided by L into D. L into D is the projected area. See, this is length and this is the diameter, right? So if you project from this side, then you will get this as a rectangle. Okay, and that is called the bearing pressure. Okay, that's why this is L, this much is L, and this much is D, and this is LD is your the area. So load divided by the area will give you the unit bearing pressure. Okay, so this is W by LD. Okay, so this is after putting the values, W is given as 5 kilonewton, 5 into 10 to the power 3, L is given as 45 and 50. So we will get it as 0.1464 is your Sommerfeld number. But to find out the minimum thickness or everything, you just have a look in the data book, that the in the data book you have to use these diagrams. Okay, these diagrams. Okay, here you see for this one, I mean, yeah, here you see, here we have a diagram. Here bearing characteristic number, the Sommerfeld number is given, but the unit they have written something like second per minute. Okay, second per minute is there. Okay, now what is second per minute? Here whatever value you get as, okay, that is unitless. But if you want to write second per minute, okay, then what you have to do is you have to you have to multiply with 60. okay, because you see here you had actually you have converted this into rps, okay, but here revolution per minute is required. Actually per minute is there here, so here this is second per minute. So this is nothing but if you let's say suppose 60 second by 60 second is there, so this will be unitless. So 60 has been already divided. So I mean just I'm not going into detail. So what you have to do is you have to multiply 60 with this to get 8.788 second per minute, okay. So first, I mean you may not do this step here in this case, so 2000 directly you can put, and then we will get this value, okay, second per minute, okay. Now that is only required to find out the value for your journal bearing, okay. Now bearing characteristic number after your Sommerfeld number you have got just 8.788. so 8.788 it will lie somewhere here, and your bearing is full bearing. So beta is your actually that angle here. You see it is written, so we see this is the bearing, okay. So this is the angle beta, okay. So beta for full journal bearing, beta is 360 degree. So this is the 360 degree, this is the line, okay. So bearing characteristic number is 8.7 some second per minute. So here it will you'll find out, and you see it will make an intercept with this line here somewhere, and this is the value of h naught by c. H naught by c is the minimum film thickness divided by your clearance, h naught by c. So this is 0.82, around 0.82. So here we have got it as this from data book figure 15.9 for this value of your Sommerfeld number. You have h naught by c is 0.82. So from here c is known 0.04. So h naught, that is minimum film thickness, h naught is this one 0.034, okay. That calculated that one. Now we need to find out power lost in friction. So power lost in friction, so a power loss in friction is asked, but I have found actually coefficient of friction. So power loss in friction is actually left in this question. Coefficient of friction will be required. After that we can find out the power loss in friction, that is left in this question, that we can find out after. Let me first explain this coefficient of friction. So again from data book, using a different diagram, this one, so 15.7, using the bearing characteristic number we get another value, which is here it is written as coefficient of friction variable, okay, or the friction variable. So rc by r by c into f, small f, and small f here is your friction variable, friction coefficient of friction, okay. So this is fv that we need to get from this table, from this figure. So bearing characteristic number is now 8.7 something, so it will lie here somewhere. Roughly we just take, so here it will this is the line for beta is 360 degree. So this is the line, here it will intercept, make intercept, and this is the value here somewhere, okay. So we can take the value as around 2.8, very near to 3. Now we have taken this 2.8. You can take anything around 2.75, 2.7, everything is okay, okay. Now fp is 2.8, so fp here is r by c into f. So fp is 2.8, so put it there, 2.8, c is 0.04, and r is the radius 25. So we'll get coefficient of friction. So power lost in friction can be found out by from this formula, kilowatt, that is power in kilowatt, that is 2 pi ns into coefficient of friction multiplied by the load multiplied by the radius divided by 10 to the power 6. If you do that, then you will get this into 33.33 we have. So multiplied by 0.00448 multiplied by this is 10 to the power 6 multiplied by load is 50, I think it was 50, sorry 5 into 10 to the power 3, and radius is 50. So if you calculate this, then you will get the friction, the power lost in friction, that is, let me find out, 2 into 23 multiplied by 0.00448 multiplied by 5000 multiplied by 50 divided by 10 to the power 6. So 0.32345 kilowatt. So this is power lost in friction. Okay. Similarly, we have another problem. Similar thing is written. Okay. Here, when we have unit bearing pressure, we have found like this. We have found the Sommerfeld number in the same way. Okay. From data book, again using this Sommerfeld number, right? This multiplied by 60 to get it second per minute. So from data book, this figure we have got H0 by C. Okay, so from here minimum film thickness H0 can be calculated by multiplying the value of C, and then coefficient of friction, again from that table, figure, we get FP as 0.9, for S as for 0.8. I mean, I can show you. So look at this. For S as for 0.8, it will be here somewhere. This is the value of FP. Okay, and similarly here for S as 0.8, so it will be the value somewhere here. Okay, somewhere here. Okay, like that. So H0 by C is 0.15 around. So we have got H0 is this one, and coefficient of friction is 0.00216. Okay, and we get power loss in friction by multiplying everything. So 2 pi ns F W R. Okay, this is the power lost in friction. Okay, so this was the discussion of your bearing numerical part. Okay, thank you.